Question 7 from the 2019 Advanced Higher Physics Examination. A Hertzsprung-Russell HR diagram is shown in figure 7a. And part A says that stars are classified depending on their position on the HR diagram. Part I, 4 stars are labelled on the HR diagram, and for 1 mark we have got to state which of these stars is a red giant. Well, first of all, the definition of a red giant is the following. A red giant has a cool surface temperature and a very high luminosity because it is large. And how do we understand that? Well, we know from the luminosity equation that the luminosity is related to 4 pi r squared, the surface area of the star, times sigma, a constant, times T to the power 4. So if we have a certain temperature, then we know the star is going to be very big if its luminosity is going to be very big. So we've got to decide which of these stars fits the category of a cool star, which means it's got low surface temperature, and high luminosity, which means it's a very big star. Well, let's start with the surface temperature first of all. So you have to be very careful with this, because if you look at the HR diagram, the surface temperature measured in Kelvin is really opposite to what we really think graphs should be. We start at the left with high temperatures and at the far right with low temperatures, so you have to be very careful. So this line here represents stars with low surface temperature. So if you're on that line there, you have a star, you're a star with a low surface temperature, so you'll be kind of reddish in colour if you're on that line there. So that gives us a choice between star D and star A. But we're told that the red giant is very luminous. So when we look at the luminosity part of the graph, you can see the higher we go, the more luminosity we have. So high luminosity stars will be up in this region here. So the only star that fits the bill there is going to be star D. So star D must be a red giant. It's got the line of cool surface temperature, red colour, and it's very up high in the HR diagram, which means it's got high luminosity. So the red giant is star D for 1 mark. Part 2. At present, the Sun is a main sequence star. It is predicted that the Sun will eventually become a red giant. Now, for 1 mark in part A, we're asked to state the change that will occur in the fusion reactions within the core of the Sun at the point when it leaves the main sequence. Well, the star we're looking at is our Sun, and it's been sitting in the main sequence for about 5 billion years, and it's got another 5 billion years to go in the main sequence. But eventually it will leave the main sequence. And why does this occur? Well, the simple statement is quite simple. Fusion of hydrogen in the core stops, and that causes our Sun to move off the main sequence. Our Sun is quite happily burning all its hydrogen. When I say burning, I mean nuclear reaction, fusing all its hydrogen into helium. And the helium is building up in the core. But in 5 billion years' time, we'll run out of hydrogen, or the Sun will run out of hydrogen, and the nuclear reaction in the core will stop. And that means it'll go off the main sequence. So for 1 mark, all you have to say is fusion of hydrogen in the core stops, and that will take it off the main sequence. Now, part B is a bit different. It says explain in terms of gravitational force and thermal pressure why the diameter of the Sun will increase as it becomes a red giant. Now, in a star or in the Sun, there's a constant battle going on between the thermal pressure pushing outwards due to the hot gases and the gravitational pull trying to contract all the matter downwards. And that battle is going on all the time. And the Sun adjusts its battle so that these two forces are equal, these two battles are equal. But let's take a look at what happens when the fusion of hydrogen in the core stops. When that happens, the core begins to collapse. Gravity takes over and the core begins to collapse downwards. Gravitational force is becoming bigger. And because there's no nuclear reaction taking place, there's no thermal energy being produced. But when the core does collapse, you're going to get that gravitational potential energy from all the matter being converted into heat. And that heat makes its way out from the core to the outer regions of the star. So that hot gas starts to expand as it goes out further, cooling down. And as it expands, its surface gets larger. And as you can see, as its surface gets larger, the temperature is going to be reduced. And therefore we see the temperature being reduced, we see it as a red outer layer of the star. It becomes a red giant. So just to recap again, explaining in terms of gravitational force and thermal pressure, why the diameter of the sun increases. Quite simply, thermal pressure overtakes the gravitational pull. When the nuclear reaction stops in the core collapses because gravitation, the force of gravitation, takes over. As the gravity pulls down, as the core collapses, then that energy, that gravitational potential energy, is changed into heat energy, which is then transmitted through to outer layers of the sun. This causes the outer layers of the gas to heat up and expand, and as it expands it becomes cooler, and we see the cool gas in terms of wavelengths as red, and the star, our sun, becomes a red giant. Question 7 continued, part B. Betelgeuse is a red supergiant star in the constellation Orion. It is 6.1 times 10 to the power 18 metres from Earth and has an apparent brightness of 1.6 times 10 to the minus 7 watts per metre squared. For 3 marks we've got to calculate the luminosity of Betelgeuse. So we go to our data sheet. You can see that the equation for apparent brightness is that one written there. It is B equals L divided by 4 pi r squared, where L is the luminosity and r is the distance which we are away from Betelgeuse in order for us to calculate its apparent brightness. So we'll put down the equation then. The equation is put down as following. The apparent brightness B is going to equal to L, the luminosity, divided by 4 pi r squared. Now we rearrange and we get that the luminosity L, we cross multiply. L is equal to the apparent brightness times 4 pi r squared. So all we need to do is put in the numbers, and we can say L is equal to the apparent brightness, which is B, and we're told that's 1.6 times 10 to the minus 7, and it's going to be watts per metre squared. I'm going to multiply that by 4 times pi times, and it's going to be the distance away which we are from Betelgeuse, r, and r is going to be 6.1 times 10 to the power 8, and don't forget to square it. And the units for that are going to be metres squared, because distance is a metre, and if you square the metres, you're going to get metres squared. So the luminosity of Betelgeuse, if we do that in our calculator, is 7.48 times 10 to the power 31. And you can see metres minus 2 and metres squared cancel out, and you're left with just simply watts, which is the units for the luminosity. Now we can cut that down to just simply 2 significant figures, and we can write the luminosity is going to equal to 7.5 times 10 to the power 31 watts, to 2 significant figures. Question 7, part B, part 2. The radius of Betelgeuse is 8.3 times 10 to the power 11 metres, and we're going to calculate the surface temperature of Betelgeuse. Take a look at our data sheet at the beginning of the exam, and we can see that the luminosity of Betelgeuse, L, which we know from the previous question, is equal to 4 pi r squared sigma t to the power 4. So that's the equation in which we're going to use. That's the equation ring there. L equals 4 pi r squared sigma t to the 4. So we'll mark that down then. L, the luminosity of Betelgeuse, is 4 pi r squared, r being its radius, times sigma, Stefan-Boltzmann's constant, times the temperature to the power 4. Now we're after temperature, so we have to make sure that we've got that temperature to the power 4 on its own. So you can see we just need to divide each side by 4 pi r squared sigma. So L divided by 4 pi r squared sigma should leave you with t to the power 4 on its own. Now we'll not work out the root of the temperature at the moment, we'll just work out what t to the power 4 is. So we've got to look up our data sheets. We already know that the luminosity of Betelgeuse from our previous calculation, the luminosity is going to be equal to 7.5 times 10 to the power 31 watts. Stefan-Boltzmann constants, we have to look up the data sheet for that. And you can see Stefan Boltzmann constant there, sigma, and that's going to be the following value. Sigma is equal to 5.67 times 10 to the power minus 8, and it's got real big units here, watts per meter squared, and K to minus 4. So that's us got our Stefan Boltzmann constant, so we can move away our data sheet out of the way. So we've got everything we need to know. The radius r is going to be 8.3, so radius r is going to be equal to 8.3 times 10 to the power 11 meters. So our t to the power 4 calculation is going to equal to L, the luminosity, which is 7.5 times 10 to the minus 31 watts, divided by 4 times pi, times, and we've got to square the radius. It's going to be 8.3 times 10 to the power 11 meters, all squared, and finally multiplied by that Stefan Boltzmann constant, so multiplied by 5.67 times 10 to the power minus 8, and you're going to have watts, meters per squared, and Kelvin to the minus 4. Now you can see that things are going to cancel out here. You're going to have the watt cancelling with the watt, and the meter squared cancelling with the meter squared from here. And you're going to be left with K to the minus 4, which is Kelvin to the power 4. So that matches up with what T to the 4 is. So our calculation is going to produce the following number. T to the power 4 is 1.528, we do this in our calculator, times 10 to the power 14, and the answer is going to be units Kelvin to the power 4. We don't want the fourth power of the temperature, we want to find the root of that, the fourth root of it, so therefore T is going to equal to the fourth root of the square, well, the fourth root, sorry, of 1.528 times 10 to the power 14, and of course the Kelvin will come out to give Kelvin on its own. So taking the fourth root of that on our calculator is going to give us 3515 Kelvin. So we've found the surface temperature of Betelgeuse. We can put that into two significant figures. We can write that as 3500 to two significant figures. And that's how you find the temperature, the surface temperature of Betelgeuse. The last part of question 7, part C. Ultimately, every main sequence star will become either a white dwarf, a neutron star, or a black hole. State the property of a star that determines which of these it will eventually become. Well, the whole thing rests on the mass of the star when it becomes a star. The mass determines what the star will end up. If it's a medium mass, like our sun, it will end up as a white dwarf. If it's much heavier, much bigger mass than that, then it will probably collapse into a neutron star. And if it's definitely a bigger mass, then it will end up as a black hole. But the key thing is what property determines which of these it will eventually become. For 1 mark is the mass.